In the last video, I came up with this quantity called the Maxwell stress tensor, which you can see right there. So it's a combination of the electric and magnetic fields. So if I was now take the divergence of the tensor, now remember this is a tensor, so it has two directions to it. So really I'm looking at the divergence of this tensor and I'm only looking at one component. So basically I'm taking the divergence, I'm summing up the divergence of say the I index, and I'm left with the J index, which can be a little bit confusing when we use Gibbs notation. But if I did this, writing this out in Gibbs notation, then I would get epsilon naught the divergence of E times the EJ component plus E times the del times the EJ component. Whoops. Don't close the brackets just yet. Minus 1/2 the J component of the del operator operating on E squared. Now I can close the brackets. And I get something similar for the magnetic fields. I would get plus 1 over mu naught del dot B, the J component of B, plus B dot del, and the J component of B, minus 1 over del J B squared. Okay, which looks a lot like what we're shooting for when we're looking at that force per unit volume. So here I wanted to take a slight deviation from what's in the textbook and write this thing out not in the original Gibbs notation, but to write it out in our index notation or Einstein summation notation. So if I was to write this out, I could write down my del. Now I'm writing as this lowercase delta with the I index on it. Okay. So on I can go from X, Y, Z. Basically, there are three, So, del 1 is dx, ddx. Del 2 is d, dy. Del 3 is d, dz, like so. Okay, so I would write down del I times this tensor ij. Now I'm writing it, since it's a dot product, I have to write it in its covariant form. And when I do that, I can write out epsilon naught del I electric field I EJ plus EI del I EJ minus 1/2 del J EI EI, like so. And now let's add in the magnetic field part. 1 over mu naught Okay, so now we've got all our I's and J's, all our indices are perfectly worked out. So the interesting thing is, so now what we're going to do is we're going to take that and put that into our force equation. So the equation we have for the force is the force per unit volume I can write out in Gibbs notation as del dot this tensor minus epsilon naught mu naught the time derivative of the pointing vector. So remember, I'm taking the divergence of my stress tensor, but the stress tensor has 2 dimensions. The divergence only sums up 1 dimension, so that gives us the other dimension for the force vector. Okay. If I want to write this out, if it's easier in index notation, then I would have Fj is del I Tij minus epsilon naught mu naught Sj d. So the time derivative of Sj. So now if I was to take the full force, so I integrate over the volume, when I do that, I basically integrate over the volume like so. Now this I went straight for the index notation to write out the force. I could have written out the force with the del operators and such, but anyway, so what you get is so this is Fj. I should be careful. If I'm using index notation, I should use the indices. So when I do that, this is the divergence theorem. And so what I should get now is the integral over the closed surface of the stress tensor. And this would be an area vector. So remember, I got to put in the index. Minus, here, if I can take the time derivative outside the integral, and what I get is epsilon naught mu naught the time derivative of the integral of the pointing vector over the volume. So if it's a static case, right, then the time derivative of any function is going to be 0, right? So it's not changing with time, it's static. So that's going to be 0. So if we take the static case, then the force that's felt is going to be the stress tensor, the integral of the stress tensor over the area. So what is this stress tensor then physically? So physically, this stress tensor is the force per unit area, which is one reason why it's called a stress. A stress is a force over an area, akin to like a pressure. So it's a force per unit area, and so that's what we get. We have this force per unit area. So now what we can do is try and apply that to electrodynamics and see what is the force per unit area you would get if you have a case of electric and magnetic fields. So I think I will stop here since the next one is an example which is kind of extensive. So I will end this video, and then the next video I'll move on to a discussion or go over an example that employs the Maxwell stress tensor.